Hello, everyone, and welcome to this week's NSERC PermafrostNet seminar. I'd like to begin by introducing today's presenter, Liam Carson. Liam is a master's student at the University of Calgary under the supervision of Dr. Brian Moorman, having completed his undergraduate degree in geography at the University of Victoria in 2022. Liam's research focuses on the effects of permafrost thaw in the mountains of Svalbard, specifically how permafrost within glacial moraines can affect slope stability. He is passionate about UAV-based remote sensing and delivering high-quality geospatial data products. Liam has a keen interest in mountainous regions stemming from his experience hiking, mountaineering, and skiing in British Columbia. Liam also has an interest in photography, aiming to capture the compelling nature of the mountains. Now, Liam, whenever you're ready.
Yeah, hey everybody. As Gabriel said, my name is Liam, and I'm going to show you my research today, which is looking at the Proglacial Retrogressive Thaw Slumping that is occurring in the Scott Turnerbreen Forefield. Here are some images of some of these events. So I'll get right into it. So studies have indicated that Svalbard is undergoing immense change, with the Arctic experiencing a higher rate of warming when compared to the global average. A rapid increase in glacial recession is occurring. Approximately 34,000 square kilometers of Svalbard, also 57% of the land area in Svalbard, is overlain by glaciers, which contributes to roughly 10% of all Arctic glaciers outside the Greenland ice sheet. Within the last 4 decades, the Svalbard archipelago has seen a decrease in glacial area of roughly 80 square kilometers per year, which indicates a 7% reduction of both land and marine terminating glaciers in Svalbard. So evidence of this profound glacial retreat can be examined in the Svalbard archipelago at the Scott Turnerbreen Glacier, which is a small Arctic glacier in central Svalbard. It has experienced rapid retreat and thinning over the last 90 years. So from 1936, the glacier's extent decreased from 4.7 square kilometers to 1.7 square kilometers in 2019. And then similarly, the glacial length has also decreased. In 1961, Scott Turnerbreen measured about 5.3 kilometers in length, but by 2009 it had decreased to 4.2. The most recent measurement in 2019 recorded the glacier at 3.3 kilometers long, indicating a retreat of over a kilometer within a decade. Furthermore, this highlights that the retreat rate in the last decade has surpassed that of the previous 5 decades combined. So there's huge amounts of change happening in the glacier. These charts just highlight the downward trends received in each of these separate areas, so area, length, volume, and thickness. But that's not the only change occurring in the glacial region here. If we move to the forefield of Scott Turnerbreen, we can look at some ice core moraine features. Ice core moraines are pretty much formed like other moraines. However, instead of the material depositing along the lateral and recession margins of the glacier, the buildup of a glacial material is formed on top of the glacial ice, creating an insulative layer that protects the buried ice beneath. And since the Arctic is characterized by continuous permafrost, this enables sufficiently low temperatures at the depth of the buried ice, and as a result, when the glacier retreats, the ice beneath the glacier debris retains its mass while the rest of the glacier recedes and ultimately detaching from the main ice body. So this is what this diagram on the left here shows. The thicker this insulative debris cover is, the more effective it is at preserving the buried ice beneath the moraine, but there are events that are causing these ice formations beneath the ground to start melting out. And this photo on the right here showcases some of this exposed ice in the forefield here. So as the climate change progresses, the rate at which these ice core moraines are thawing can impact the nearby fluvial systems and alter the summer hydrological regimes of the surrounding area. So analyzing the topographical change can provide insights into how Arctic landscapes are reacting to increasing temperatures. So this diagram here showcases how some of this topographic change can occur. So this right here is topographical lowering. We're seeing some of that. We're also seeing a lot of mass wasting events, such as active layer detachments, which help influence the start of melt of these ice core moraines, and then also a lot of retrogressive thaw slumping as well, which is what this study will primarily focus on. So in continuous permafrost regions, buried ice remains stable as long as the sediment cover maintains a thickness that keeps the temperature at the ice sediment boundary below 0 degrees Celsius. However, when the temperatures rise above average, the active layer expands, which could potentially reach the top of the buried ice during exceptionally warm summers, which influences surface destabilization through ice core melt. Though this thickening of the active layer causes a pretty significant threat to the ice core health beneath, the melt caused by mass movement and erosion that exposes this buried ice, such as active layer detachments, is much more common. Well, moving on to retrogressive thaw slumps, this is primarily what my study is looking at. When these ground ice deposits melt, significant changes occur, which is what the study is observing. With the melt occurring, the introduction of water into the hill slope can decrease the cohesion between the particles and influences downward movement in the form of a retrogressive thaw slump, which is characterized as a water-induced moderate pace landslide. And this image here just shows a before and after thaw slump had occurred. So the 2018 imagery is from Eric Mannerfelt, who's a PhD candidate at Oslo University. And then this 2024 imagery was flown by me, drone photogrammetric survey in July of last year. So you can see there's tons of change happening in this forefield. This specific thaw slump is known as STB1 in my study, and this video just showcases another view of STB1. You can see myself in the top right-hand corner up here, flying the drone. And this just gives you a bit more scale into how some of these events are progressing. You can see a lot of water, a lot of moisture at the bottom of this thaw slump. So this is primarily how these sediment fluxes can enter these rivers and lakes and streams below these thaw slump events. So moving on to the characteristics. So sizes of these thaw slumps can vary from less than 1,000 square meters to roughly 1 square kilometer, while the headwall retreats can range from a few centimeters per year to tens of meters per year, depending on the topography and ice content of the region. Thaw slumps commonly form what is known as a thermocerc, which is an amphitheatrical depression created by the excavation of material through hydrological activity from the melting ice deposits and thawing ice-rich permafrost. You can see an example of this thermocerc on the image on the right here. And then another important feature of thaw slumps is that previous studies have indicated that they are also a polycyclic process. So this means they can transition from being active to stable with the potential to reactivate once again. However, most thaw slumps only complete one cycle of this process before becoming permanently stable. And this stability often occurs from when the ground ice has fully melted out or when it becomes covered by sediment, which effectively insulates it from further thawing. And then lastly, when thaw slumps are active, they can mobilize large volumes of sediment into the downstream environments, which can significantly alter the hydrology, geomorphology, and ecosystem dynamics downstream. So there is lots of change going on in these specific landforms. So this prompted me to do a study on them. The significance of the study is recent studies have concluded that the increase in thaw slumps occurring in the Arctic are impacting these fluvial systems and changing the summer hydrological regimes of the areas. Scott Turnerbreen specifically was the focus of a study in 2001 regarding ice core melt, but the study only used air photo analysis and field observations. And since 2001, which is over 2 decades now, there's been huge advancements in technology, and climate change has progressed pretty rapidly as well since then. So this indicates a need to go back to this site and reassess the change occurring in the forefield. And then I also want to highlight that there's been limited academic research using remote sensing coupled with geophysical methods to survey the ice core moraine deformation that is occurring, especially on Svalbard, but specifically in the Scott Turnerbreen Forefield. That's never been done. So this study will be the first to do that here. So moving into my objectives, number one was to determine the magnitude of topographical change, which is in the glacial forefield of Scott Turnerbreen, using change detection analysis with aerial imagery. So this consisted of analyzing the area loss, the volume loss, and the rate of headwall retreat occurring at individual sites in the Scott Turnerbreen Forefield. So that's what I will focus on first. So just to give you context on where these sites are. So Scott Turnerbreen is the glacier highlighted in the center of the image you're seeing now. And this is a small Arctic glacier located in central Svalbard. And then I also looked at Longyearbreen, which is another glacier about 13 kilometers northwest of Scott Turnerbreen. And I looked at Longyearbreen just to see if the observations that were seen in the Scott Turnerbreen Forefield were also occurring in other forefields in the area. So these are the two study sites of my research, but first I'll talk about Scott Turnerbreen. So this is the map of the forefield. You'll see 3 thaw slumps highlighted in this forefield. Now these are the 3 that you've seen that were active during my survey. So you've seen STB1, that was the video I just showed you previously, but then we also have STB2, which is a bit smaller, and then STB3. And again, these were the only ones that were active during my 3-week observation period. So these are naturally the ones that I'll be focusing on in my study. I used a drone to capture over 65,000 images during the summer between July 6th and July 27th. I used a DJI DRTK2 base station for GNSS correction, and then I used a DJI Mavic 3 Pro thermal with a DJI RTK receiver attached on the top. So this allows the drone to communicate with the base station, and the base station allows real-time corrections to the drone locational data. And then I also want to highlight in these images, you can see the little Scott Turnerbreen in the background. It's quite small now. The pictures don't deceive you. It's just a bit of a sad sight looking at it from this angle, but it created a massive forefield. So that's kind of where the basis of my study is. So these flights provided me with approximately 23 digital elevation models during July, and I was able to use the 2018 drone imagery from Eric Vanderfelt, as I mentioned previously. But unfortunately, some of the 2024 models had elevation errors, specifically doming, which is a radial elevation distortion in photogrammetric DEMs. So the doming in the 2024 models was pretty hard to identify through just visual comparison. However, when subtracting the 2018 DEM with the 2024 DEM, the error is much more clear, which you can see here. The left side is before the correction was done. So you can see this kind of radial distortion in this model here. But to fix that, I used a Newth-Cobb method of co-registration, which is a paper that came out in 2011. And it has kind of been the basis for these co-registration methods since then. So it was pretty well documented that this works pretty well. So yeah, you can see the before correction, and then on the right side, you can see after the correction. And this looks much more what I wanted to get out of these models. You can see the glacier decrease in thickness, about 10 meters in some of the more red parts. And then you can see a little bit of erosion or elevation decrease going through the center of the DEM from the river, which you can see here. But obviously the valley walls are not going to increase in elevation by 10 meters. So this is obviously a better model to look at. Moving on to field observations. So these are some of the observations I made while I was in the field in both the summer of 2024 and then also a couple months ago in February and March. So the group of photos on the left are just showcase some exposed ice within the headwalls of certain slumps. The ice bodies had roughly 1 to 2 meters of exposure in height, and then also ranged about a couple meters to about 10 meters in width for the exposure. And then they were also about 1.5 to 2 meters below the surface. So they're pretty near surface ice structures. And then the images on the right here just showcase some of these thaw slumps. So STB1 is on the top left, the STB2 is on the top right, and then STB3 are both photos on the bottom. And that just gives you a bit more context in the scale, and then also just how much fluvial movement is occurring at the bottom of these thaw slumps. And it gives you a bit more context in the sediment mobilization that's occurring in these morphological features. So here we have the 3 thaw slumps you've seen previously. We have STB1 on the left, STB2 on the top right, and then STB3 on the bottom right. This is the elevation change or visualization of the volume loss that has occurred between July 6th and July 27th for each of the thaw slumps. The red color indicates the elevation decrease, while the blue color indicates elevation increase. So obviously you're seeing mostly a lot of volume decrease occurring in these thaw slumps, primarily in the head walls. The dark reds here are pretty much outline the head walls. And then the blues here are pretty much like some type of solifluction lobes or just some kind of lobite features that form, which slightly increase the elevation. But you can obviously see that the STB1 is the highest or most amount of elevation loss that has occurred during this time frame. And you can also tell that STB2 is the least, but we'll get a bit more into that relationship in the coming slides here. So this essentially shows the same information as the previous slide, but this just highlights the head wall elevation loss, while the previous slide just shows some of the basal movement that's occurred here. We've cut that out fully just to give you a bit clear view of what's going on here in the head wall specifically. And then again, you can see STB1 is a lot more volume loss in the head walls. This is about 10 meters here, so quite a huge amount of head wall retreat as well, whereas this is about a couple meters, 2 or 3 meters at most. So here we have an image that shows thaw slumps as previously shown. Again, we have the STB1 to STB3, but in these images, the colored lines indicate the position of the head wall at a given date. So for example, on July 6th, the red line, or the July 6th position of the head wall is indicated by the red line. The July 11th is indicated by the orange line, and then the yellow line indicates July 16th, and so on and so forth. So you can just see the rapid back wasting that's occurring from this head wall retreat on individual days. But then I also came back in February of this past year and did some area measurements or head wall. I traced the outline of the head wall with a GPS and collected this shaded region here. So this is the new head wall location. So this shaded region here essentially represents the area loss that occurred between July 27th, which was the last date of my survey, and then up till September 20th, roughly, which was pretty much the date where temperatures dropped below 0 in Svalbard. And as a result, these thaw slumps would be inactive for the rest of the season. So this is about a month and a half, 2 months of area loss that's occurred here. So again, I just want to point out it's so hard to do this type of research with just 3 weeks of continued surveying. As you can see, this is from the red to the purple. That's all the area loss that occurred in the 3 weeks. And then following that, it's just a huge amount of area loss. So yeah, it's quite tough to accurately characterize the behavior of these thaw slumps in such little time. But nonetheless, I was able to calculate the area loss, the volume loss, and the rate of headwall retreat. And as you can see on the right, STB1 is the highest of all three, while STB2 is the lowest of all three. And that is again shown in this cumulative volume loss over time chart. STB1 is in red, and that just kind of showcases how much more volume loss this specific thaw slump saw compared to the other two thaw slumps. So a huge amount of change going on here. So moving on to rate. So these are transects and each of the headwalls of the thaw slumps. These transects were used to calculate the rate of the headwall retreat. So the number of the transects used to calculate the rate was dependent on the size of the thaw slump itself. So for STB1, due to its larger size, I used 4 different transects. For STB2, I used 2. And then for STB3, I used 3 again, just due to its larger size. So based on the transects from the previous slide, I was able to calculate the total distances from the headwall retreated along each transect for every survey. And then using these distances, I was able to calculate the rate per day along each transect and average them, giving me a total rate for each thaw slump. So these are these results at the bottom here. Again, as I said previously, STB1 is the highest at 0.29 meters per day, STB2 at the lowest at 0.13 meters per day, and then STB3 again in the middle at 0.22 meters per day. This image here you're seeing is a collection of slope profiles for each of the thaw slumps. These are essentially just measuring the slope on different days. So the dark red lines indicate the slope on July 6th, and then the yellow lines indicate July 27th. And then also I want to keep in mind that the x-axes are definitely different scales. So even though it looks like this headwall retreat is much greater than STB1, I can assure you that STB1 definitely saw a lot more retreat in the headwall. So that kind of brings me into what is causing these events to occur. So here we have 2 charts. The top one's looking at temperature versus cumulative volume loss. We have air temperature in blue and then ground temperature in orange. That's minus 15 meters or 15 centimeters below the surface. And then I also have ground temperature at about 155 centimeters under the surface. And the 2 different ground temperatures are just kind of to show surface level change in temperature, then also the temperature change that is occurring around the depth of the buried ice that we're seeing in the headwalls. So you can see that surface level ground temperature pretty closely follows air temperature movements. So these 2 are pretty well correlated. But if we look at the temperature increases throughout the survey period of July 6th to July 27th, we can see an increase in volume as the temperature spikes. So around July 20th, we see an increase in temperature, and then around July 23rd, we also see an increase in volume loss occurs. And then a following one, there's a spike in air temperature around July 24th, 25th, and then again, we see increase in volume loss here. So there's a high correlation, especially with STB1. But what is interesting is the precipitation. So if we look at the lower chart here, we see a precipitation event occur around July 7th, but that appears to have pretty minimal effect on the overall volume loss, as you can see. So this brings me to believe that there's a really low correlation between these 2 data sets, and this is interesting, as previous studies have indicated that these precipitation events are primarily or really influence the activity of these thaw slumps, and that's primarily due to the decrease in cohesion that the added water into the system causes. But that's not what we saw here, and that's likely due to it's a pretty small overall precipitation event. It was only 2.6 millimeters, so relatively small, and previous studies have indicated the relationship between precipitation and thaw slump activity. They experience greater precipitation events. So that could be one reason. And then another reason, this precipitation data was gathered from the closest nearby weather gauge station, which was the airport. And that's about 15 kilometers away from my study site and about 200 meters lower elevation. So there could be some discrepancies between the location of my survey site and the weather data. So moving on to objective 2, this is to ascertain whether the greatest rate of topographic change can be attributed to the erosion or slope failure of ice core moraines using GPR and field observations. Firstly, I want to highlight that I was able to take some thermal photos during my surveys. And now these are the same thaw slumps you've seen previously, but in these images, the lighter pixels indicate a warmer surface, while the darker pixels indicate a colder surface. And in this case, the cold or the dark pixels largely indicate some cold meltwater emanating from the head walls. And if you look at STB1 and 3, you'll notice this sort of tree branch-like dendritic drainage pattern that is coming from the head walls of both of these thaw slumps. However, if you look at STB2, you'll notice that there's really not a lot of water at all in the system, let alone the dendritic drainage pattern. So it's interesting, this is the only thaw slump that we did not see any exposed buried ice in. So as shown by the pictures here, we have STB1, which is quite a large amount of ice in the head wall. And then the same thing for STB3. That's a piece of ice I chipped out from the thaw slump. But again, we didn't find any ice in STB2. So this leads us to believe that these dendritic drainage patterns we're seeing here in both of these thaw slumps are direct results from exposed buried ice that is melting, which is feeding these drainage systems. Now, that's not to say that STB2 has no ice in it at all, or that it wasn't once driven by exposed buried ice, but that's as far as our field observations go, we didn't see any exposed ice evidence. So to answer this question of what is driving STB2, we wanted to do some GPR. So this GPR was done in March of this last year, and it was done by dragging a MALA system, a rough terrain antenna, behind a snowmobile. We had one person driving the snowmobile and then another person operating the GPR. You can see the transmitter here and then the receiver here. So it looks kind of like a long rope and you tow it behind the snowmobile. We used both the 25 megahertz antenna and the 100 megahertz antenna. We originally wanted to do the 50 megahertz antenna, but that was unfortunately not available at the time of the survey. So the goal of the GPR was to determine if I could see any buried ice in the subsurface or help identify if these thaw slumps were developing due to melting ice or thawing permafrost. But unfortunately, the data from the GPR proved to be pretty insufficient, and the majority of the radargrams are unusable. However, this radargram that I'm showing you here is located near STB3, which you can see here, and it kind of indicates some sort of subsurface structure you're seeing here. And we have the bottom of a potential ice body and then a top of one. It roughly extends from about 2 meters below the surface to about 7 meters. So it would be in the range or the dimensions of an expected ice body. But again, the GPR radargram was pretty hard to tell. It was pretty hard to tell from this radargram what this subsurface structure was. However, the observations from the head wall that you can see in the top image here of buried ice, we have one exposure of ice documented on July 27th, and then another one just about a couple meters southwest of that on March 30th. So that leads me to believe that there's this sort of linear or laterally extended subsurface ice structure that goes pretty much directly towards the GPR transect that I did. So if this subsurface structure extends laterally for about 30 meters, then this likely would be an ice body. But again, it's too hard to tell. And then, so moving on to objective 3, which was to determine if these occurrences are localized to Scott Turnerbreen or if they're occurring in other forefields as well. So to do that, as I mentioned previously, I was able to get some drone photometric DEMs from 2018 from Eric Mannerfeld of both Scott Turnerbreen and Longyearbreen forefields. So this allowed me to do a comparison between the two DEMs between 2018 and 2024. And I was able to find the total volume loss associated with thaw slump activity between this time frame. Between 2018 and 2024, the percentage of volume loss associated with thaw slump activity in the Scott Turnerbreen Forefield was about 11.6%. The rest of this is likely primarily hydrological erosion in the main river outflow from Scott Turnerbreen, and then also some other smaller mass wasting events. But the percentage of volume loss associated with thaw slump activity in the Longyearbreen Forefield was about 57.6%. So there's just a ton more thaw slump activity associated with Longyearbreen. And that's primarily due to this large thaw slump occurring here in the center of the forefield. This specific thaw slump was about 2.6 times larger than the STB1 thaw slump in the Scott Turnerbreen Forefield. So it's massive. And yeah, it was still active at the time of my survey. So it's been going on for a couple of years. So based on these results, we can assume that the observations occurring in the Scott Turnerbreen Forefield were also occurring in the Longyearbreen Forefield. But again, I want to highlight that the Longyearbreen Forefield is about 1 square kilometer smaller than the Scott Turnerbreen Forefield. So there's a lot less area of the potential volume loss associated with the forefield. So as a result, we see more movement and volume loss associated with other factors in the Scott Turnerbreen Forefield, such as hydrological erosion or other mass wasting events. But again, that's not to say that the Longyearbreen Forefield isn't experiencing the same things as the Scott Turnerbreen Forefield. You can see here, this is a thermal image of the Longyearbreen Forefield. We have LYB1 here, and then LYB2. This is the large thaw slump. And you can see the same sort of dendritic drainage pattern that we saw previously coming out of the headwalls of each of these thaw slumps. So based on the Scott Turnerbreen results, we can assume that not only were these thaw slumps active at the time of the survey, but they're also likely driven by exposed buried glacial ice, which is feeding these dendritic drainage patterns we're seeing here. So that brings me to my conclusion. This study was the most comprehensive study of mass wasting dynamics in the Scott Turnerbreen Forefield. It is also one of the first to utilize remote sensing methods in conjunction with geophysical methods to provide a surface subsurface analysis of ice core moraines in Svalbard specifically, even though the GPR was able to only provide 1 point. And then the findings contribute to a broader understanding of permafrost degradation and geomorphic change in glacial forefields, with implications for Arctic landscapes and evolution in the warming climate. And then also this study indicates that there is evidence of extreme ice core moraine degradation occurring, and it's also prevalent in multiple forefields in Svalbard. However, while our study encompasses multiple forefields, the two proglacial areas assessed exhibited low spatial variability due to their close geographical proximity. So we recommend future studies utilize this data to conduct a broader investigation of Svalbard's forefields and determine if the moraine degradation is also occurring elsewhere within the archipelago in various climates and geological structures. And that is all I have for you guys. I want to thank you so much for listening, and thank you to PermafrostNet for hosting this.
Thank you for that great presentation, Liam. I'd like to open the floor up to questions. So,
Hi, Liam. Thanks for this really good talk. I was wondering if, I don't, maybe I missed this, but did you do any accuracy or precision assessment on your point clouds? And yeah, how did that look?
Yeah, so I did an uncertainty assessment, which essentially used the stable terrain of the surrounding forefield. I essentially separated the thaw slumps from areas that I assumed to be stable and used essentially, if you've heard of XDEM, it's this Python plugin that allows you to assess the uncertainty of your DEMs using the stable terrain method. And yeah, produce, and the individual, I can go back to so here we have the uncertainty on the bottom right of each of the images. The STV1 images had about 2 centimeters of uncertainty, and then for 2 we had 4 centimeters, and then for 3 we had 1 centimeter. So pretty low uncertainty.
Thanks. And did you say that you co-aligned your data sets?
Yeah, I used a NewsCobb co-registration method.
Thanks.
Yeah.
I have a more broad question. Do you know, or could you give some examples of how this might be applied to more generally buried glacier ice that's not necessarily in a forefield anymore?
It's tough because I think if you look at the geology of the forefields compared to like somewhere in Canada, northern Canada, that hasn't kind of seen a glacier for thousands of years, the geology is so much different, and I believe they would just react very differently. Looking at some of the studies from Canada, usually in Canada there are a lot, or other non-forefield related thaw slumps are much more large than some of these thaw slumps we're seeing in these forefields. But are you talking about like permafrost thaw related thaw slumps specifically, or just like in
Yeah,
general?
I was kind of thinking of the slumps that are pretty prevalent in the Mackenzie Delta right now. And things
Yeah.
like that.
Yeah, I mean, you could definitely use the same imaging techniques. It's pretty simple. You just kind of fly a drone and every couple of days and assess the change that's occurring. So there's already studies that are doing that and have done that for a while. But the behavior that we're seeing in the Scott Turnerbreen Forefield is going to be pretty unique to Svalbard, and specifically some of the central Svalbard geology of these forefields.
I see. So it can be very, very location dependent.
For sure. Yeah.
All right, Hossein, you have a question?
Yeah, thank you, Liam. It was a great presentation. I do really like that. And maybe I missed that, but I'm just wondering what's the frequency of GPR antenna that you use?
We had the 25 megahertz and then we had 100 megahertz. The 25 was pretty much unusable though. The one you saw there was a 100 megahertz antenna. The 25 just was way too coarse to see anything underneath. And then the 100 it just had a lot of noise. So that was the only usable one the radar gun we could get out of it. So
And did you just have some assessment of the signal to noise, SNR, I mean, signal to noise ratio?
No, I didn't. It was a very quick and dirty GPR assessment. We only had very limited time to get it done, so we kind of just wanted to bang it out, and yeah,
Yeah, thank you.
no worries.
I'd like to thank you again, Liam, for that great presentation. Have a good day, everyone.
Thank you.